Good morning, everybody. I'm very happy to be here to present my work. So I'm Alice Chillet, and I'm in my third year of my PhD, and the subject of my PhD is sensitive device identifications through learning of radiofrequency fingerprinting. So my supervisors are Robin Gerzaguet, Carole Desnos, and Mathieu Gauthier. Carole is a member of Vaader teams, and Robin, Mathieu, and me are the members of IRISA laboratory in Granit. So first, I would like to introduce the topic. So we will identify some things thanks to faults. So for example, on this picture, these guys look like Johnny Hallyday. His name is Johnny. He's dressed like Johnny and he sings like Johnny, but he doesn't have the same fault as Johnny. And this is not Johnny, this is a sosie. So in this PhD, to introduce the context more scientifically, so we want to do a sensitive device identification. And to do this, we are in Internet of Things context and security. So we want to do an identification of device with a reduced header, and we want a not spoofing identification, and we work with embedded system. So if I take an example of what we want to do, we want to identify a device under surveillance, and this device implement a security mechanism, and this mechanism is, for example, it changes its MAC address very often. And because of that, it's not possible to identify the device with its MAC address. So we propose to identify it with his radiofrequency fingerprint. So this identification solution is interesting because we could not, it could not be spoofed because this is very, this is a unique signature of the component. Then this identification solution is not dependent to the communication protocol. So this is interesting. We will do some assumption related to the identification system. We wanted robust in a variable environment. For example, if our device changed the place in a room, or if we change the day, or I don't know, we want to be able to classify the device again. And then we want an identification solution embedded with an embedded or mobile. For example, that a laptop could be fine for us. So if I want to resume my PhD with 4 points, so the objective is to recognize radiofrequency devices. So this is an identification problem. And to do that, we propose first to using a genetic algorithm instead of deep learning solution, because the deep learning is the most popular solution used in the state of the art. And we want to reduce the complexity of the identification or classification solution, and the genetic algorithm allow to reduce the complexity. And then we propose to analyze the recent database, and this analyze help us to propose a RiFyFi virtual database generator, because we think that the generator help to avoid some problem of the database. So first I will present the state of the art, and then I will present the Tangled program graph for the radiofrequency fingerprint identification. Then I will present the work on the database generator, and then I will conclude and give some perspective. So first, what is radiofrequency fingerprint? So this is a unique signature created by the hardware component of the transmission chain. So here you have the transmission chain with a different component, and all of those components have some distortion function. And for example, for example, the signal that we will emit is here, and it's a composition function of the different distortion function of the component in the transmission chain. And the signal used for the identification is here and here. And this signal is the composition function of the transmitter fingerprint, so this part, the channel here, and the fingerprint of the receiver here, because and all of this function could impact the signal that we will use for the classification. So in the state of the art, we have different solutions for identification, and the first one and the oldest one is the parametrics method. So first we estimate some features, and then we use a classifier to estimate the device. However, this solution shows some problem because we have some difficulty to compute the estimator, and the quality of the estimator is totally linked to the quality of the classification. So next we have some deep learning solution, and deep learning solution highlight non-linearity. So this is very interesting things, and we don't have to we don't need information, and we don't need to create a good estimator to estimate features. So this is interesting, but the deep learning has learned the channel. So this is very difficult because remember that we want a solution robust in a non-variable environment. And if the deep learning learned the channel, if the device changed place, the deep learning the neural network will be not able to classify device as good as if we are in static solution. So then the deep learning solution, some authors propose to add channel equalization or data augmentation to the deep learning solution because they try to reduce the risk to learn the channel. And those solutions are good, but we need a lot of data to train, and we have to create a realistic augmentation, and this is not really easy. And then we have some hybrid method where we combine estimate features and deep learning solution. And this solution helps to reduce the size of the network. So in this PhD, we focus on deep learning solution, but we take in mind that we want, we have some problem about channel, and we take in mind that we want to reduce the complexity of the identification solution. So here, this is the state of the art about database. So we have many databases, and this is just a selection of database for radio frequency fingerprint. So here you can see that we have some database with few devices, and the database with many devices are not public, and this is a big problem for us. But and recently we have this database called RiFyFi. And this database is a big one, and when the author create the database, they want a very large database, and so this is an interesting point. So now I propose to present the Tangled program graph for radio frequency fingerprint identification. First, I will present the setup description, and then result and conclusion on this part. So first, about scientific logs and solutions. So first, we have to decide what type of database we will use, and we have many references in the state of the art, as I presented before. Some of them are private, some of them are public, real or virtual. And we have a lot of difficulty to build a good database, an exhaustive or multi-aspect. So yeah, this is difficult. So we decide to use the WYSIG database because this is a recent one. Then this database is separated in two parts for the training and the test. And we have to choose a network. So we have already many references, particularly convolutional neural network and other architecture. But we have some problem about the complexity because for our application, we want to learn on CPU, but the learning is very long because we have more than 1 million parameters, and for our application, this is a little bit too much. So this is difficult for embedded system. So we propose to use Tangled program graph and compare with the CNN of the state-of-the-art. So first about WYSIWYG database. So this database and the dataset we are used for this paper is composed of 6 transmitters in blue on this picture. And this is the representation of the room where the transmitters are located. And on red, you can see the receiver, and on orange too, but this is not the same references of the receiver. So we have information about the transmitter and receiver location and references, and we know that the signal are Wi-Fi. And the data comes from different day and different receivers, so this is interesting. And interesting point, another, is that the set doesn't change between 2 days, so this is good for the reproducibility and good for having reproducibility. Okay. So we try to do the classification with Tangled program graph. So what is it? So this is a reinforcement learning model based on genetic programming technique. Maybe some of you know this TPG. So it's composed of a program. This is assembly-like sequences of instruction. And then you have some action to classify the signal in the class 1, for example. And then you have some teams. This is control flow. So here we select a number of sequences. Here, so the sequences for us is a part of signals. And then we take one sequence, and this sequence pass through the graph. And we execute all of the program, and at the end of the program, we obtain a score, and we will follow the branch with the best score. So, for example, this is this branch, and at the end, we have the action to classify the sequence here in the class 1 here. After all the sequences pass through the graph, we have a new iteration or a new generation, and this is at this time the genetic programming technique do its work, and so some branch disappear and some branch appear or are copying, mutating, and genetic algorithm works. At the end, so the most advantages of TPG is that the complexity depends on the separability of the different classes. So if the problem is difficult, the complexity of the graph will grow, and but if the complexity of the task is very few, the complexity of the graph will be few too. So now I will present the result, Tangled program graph, and deep learning comparison, and then I will talk about the influence of the channel. So in this paper and in this work, we try to compare the network convergence speed between convolutional neural network of the state-of-the-art and the TPG. So in this picture, you can see the F1 score evolution during the training in function of time of the CNN on GPU here, the CNN on CPU here, and the TPG on CPU here. And we can see that the TPG has a fast F1 score progression during training phase on CPU, close to the progression of of CNN on GPU without using GPU. And this is very interesting because remember that we want to do an identification with an embedded system, for example, a laptop, maybe without GPU. So, sorry. Now it's work for during learning, but how it's work during test. And so this is the confusion matrix obtained for with the CNN, and this is the confusion matrix obtained with the TPG for test in same condition, but not with the same data. And the results show that we have good results with TPG, and the matrices are very close. So we can conclude that the TPG is able to classify transmitters. So next we have studied the influence of the channel. So this study is about how we can analyze the database, but we have proposed other results, but this is the only one that I will present today. So on the influence of the channel, we try to train the network with the signal from day 1, and then we test with the signal from day 2, 3, 4. Okay, and this is the result obtained with the TPG, but we have similar result with CNN, and this is just to show that it's exactly the same with TPG. So this confusion matrix show that we have some difficulties to generalize the training with other environmental conditions. And so we propose to do a physical augmentation, because remember that the signal used for the classification is this signal, and this signal is composed to the radio frequency fingerprint of the receiver, but we use the same receiver for all the training and the test. This is the channel, so maybe the channel could change between day 1, day 2, and day 3, 4. And this is the part of the signal that we use for the classification. So we propose to do a physical augmentation, and this physical augmentation is due with training on day 2, 3, and 4, and we test with signal on day 1, and we can see the confusion matrix is better. So the conclusion is the physical data augmentation reduces the dependence of the channel, but we can see that this is not enough. The conclusion here is that the physical data augmentation helped to reduce the dependence of the channel. And so this is not enough, because we can see that the WYSIG database is created for exploration of radio frequency fingerprint identification, and this is how authors want to create the database. But we think that we need more flexibility. For example, here, if we have, I don't know, maybe 10 days or 100 days, the confusion matrix will be, I think, better. So we think that we need more flexibility to explore database design and impact on classification. To conclude on this part, the network classification accuracy in a particular context is linked to the quality of the database, of the training database, to represent this context. For example, if we want to recognize some picture of Jack Russell, this database is very good. But if we want to recognize picture of dogs, this database is not good, because we are not able to recognize all of dogs, all of type of dogs. And we have exactly the same problem with issues with our database. And so the conclusion of WYSIG work and our exploration of the state-of-the-art is created a real database is a very long process. And so we propose to use some radio frequency fingerprint model to create database and be able to explore how we can design real database. But this is an exploration before the creation of the real database. So now I propose to present RiFyFi virtual database generator for radiofrequency fingerprint. First, I will present radiofrequency model and generator. Then I will present the results and in the interest of this point. So I know that you are not a specialist of an expert on the radiofrequency transmission and radiofrequency fingerprint model, so I will try to be just a little explication. So this is the objective is to modelize the behavior and the distortion of this transmission chain, and for all the components. So we have 4 different behavior and distortion. This is the EQ imbalance, the carrier frequency offset, the phase noise, and the power amplifier. And these 4 radiofrequency fingerprint and behavior are implemented in the model to generate database. So we have created a database generator, and this database generator is the flow is like this. So first we decide the number of transmitters that we want to simulate. So maybe, for example, 6. Then we choose what type of data we want to transmit. So we have 3 choices. The first one is to transmit a preamble data. So for example, in the preamble scenario, we have always the same sequence for all radio, all transmitter will emit the same sequence for all transmission. Next, we have the MAC address solution. So in MAC address scenario, each transmitter transmits a specific sequence as a MAC address. And in payload scenarios, we transmit random sequence, and at each transmission, this is a new random sequence, and this is random for all radio, all the transmitter. Then we add the radiofrequency fingerprint. So this is here we can choose to add just one fingerprint, for example, the CFO or the power amplifier. Or we can choose to add all radiofrequency fingerprint to modelize a real transmitter. Then we can add the channel. So in channel, we can add only level of noise, for example, 20 dB or 10 dB or 30. Or we can add a channel with a channel model used in this part. And then we have a block for the receiver model, but this is not implemented in this database generator, but we can do this. And this is very interesting because, for example, we can create 1 receiver or 2 or 3. And then we have a shaping block, so to normalize, shuffle, and create the train and the test set with the label. So this is the framework that we use for the classification and use to create a database. So first we use some files to create and define the database scenarios. And the database generator will use this file to create the database and the label. And this database is used to train the network, and we can choose the parameter of the network, for example, the name of the network that we want to use. We have implemented 3 or 5 different network in this framework. And we can choose, for example, the number of epoch, the size of patch, or the size of input of the network. At the end of the training, we saved the network, and we saved a file with the F1 score evolution to do the graph that I've presented before. And at the test side, so we can choose to use the same database that we have used for the training or another to, for example, try to see that if the network is able to generalize the classification. And then we upload the network and do the test, and we will compare the label, the true label, with the estimated by the network to create the confusion matrix. So now to present the result, I will present the result lonely. So here we have only CFO analysis. So we use we decide to create only two transmitter scenarios. So we have transmitter 1 and transmitter 2. The transmitter 1 and transmitter 2 send a preamble data. So this is they send always the same sequence, and this is the same for the transmitter 1 and transmitter 2. So the only one difference between the transmitter 1 and transmitter 2 is the CFO. And the CFO here, the mean value is 300 Hertz. And we select two different CFO for the radio transmitter 1 and transmitter 2. For example, in the 5% scenario, we have this. This is better if I say this. So here we have a large gap between the two CFO of the transmitter 1 and transmitter 2. And if we look at the different co-evolution during the training in function of time, we can see that the network is able to learn very quickly how to classify the transmitter. Now, if we look at these scenarios, so in this scenario, the gap between the CFO of transmitter 1 and transmitter 2 is reduced. And because the gap is reduced, this is more difficult for the network to separate separate the transmitter, and we can see this on this curve because the network takes more time to train and be able to classify transmitter. So we can do a same analysis for power amplifier. So this is just the parameter used for the power amplifier, but just remind that we have different scenarios, 5%, 2%, 1, 0.5, and 0.3. And we have different parameters, and we have 4 radio in this case. So we implement a Saleh model here for the 5 to 0.3%. And we can see as a CFO that the time to train the network is increased when the similarity between the transmitter increase. I don't know if it's clear, but when I was in 5%, the similarity between the transmitter is large. The gap between the transmitter is very large. And when I was 0.3, the similarity is very important. And so when the similarity is very important, the network has some difficulty to train. And then for the power amplifier model, we decide to implement another model, and this is a model based on measurement of power amplifier. And so we have 2 different models, a model with close radio frequency fingerprint and a model with far radio frequency fingerprint. And this is interesting to see that the results are not totally far to the result obtained with the Saleh model. And this is interesting to present this because it proved that the interest of the database generator, we can implement another some other models, and for example, measured model. So now, in this part, we have combined all of impairments, and we can ask ourselves how close radiofrequency fingerprint of 6 devices can be. So just to do that, we have implemented the radiofrequency fingerprint of the 6 transmitter like this. So for example, for 5 constant, we have the mean value, and the transmitter 1 is at this value, the transmitter 6 at this value, and all the gap between transmitter are equal. So the gap between transmitter in 5% is more than when we have 3% similarity. And in this situation, so we can see that, for example, for 1%, we are able to train the network, but in the test part, the network is not able to separate radio transmitter. So we have an overlap on training database, and this is the limit of the neural network to be able to separate radio transmitter. Now we can ask ourselves how many signals do we need, because in the state of the art of database, some author proposed to have 100 signals. Some author proposed to have 2,000 signals, and we are not able to know how many we need. And so this study is about this point. So the objective here is to analyze the F1 score in test when we are reach 98% during training on training data set, and what is the F1 score during on the test side. So here we have the number of the signal during use for the training in the training set, and this is the F1 score for the test. And yeah, so we can see that, for example, for 2% for the scenario for 2% similarity, we need more time. We need more signals to reach the same F1 score as, for example, 4% with 100 of signal, because when the similarity between transmitter is important, the network has to see more data to be able to separate transmitter, because this is the issue for his it's more complex. And then we ask ourselves how many channel realization should we have when we want to be able to separate signal in test. So to do that, we augmented the number of channel view in training, and we test on 100 EVA, sorry. So this is two different channel model. Just this is not the same channel model, and so we test on the 100 EVA model channel, and we augmented the number of ETU channel during the training. And so here we have two interesting points that we have seen before, that if we augmented the number of signals, it will increase the capacity of the network to separate transmitter. So in these 2 points as just one channel, but here we augmented the number of signals, and just to show that augmenting the number of signals is good, but it's not enough. And if we compare this point and this point, here we have 900 signals. Here we have 1,000 800 signals, as like here. But here, the difference between these 2 points are very, very important, and this is due to the fact that we have 2 channels and not just 1. And so those curves show that this increasing the number of channels help the network to learn the radio frequency fingerprint and not focus on the channel to learn to classify the transmitter. So to conclude and give some perspective, so first the objective is to identify radio frequency devices. So we use the radio frequency fingerprint identification, and we have seen that the network are complex. So we propose to use a genetic algorithm instead of CNN to reduce the complexity and and we have shown that we have a fast F1 score progression close to the progression of the CNN on GPU. So this is interesting for us. Now we can imagine that we will test the reproducibility and flexibility with other devices when other devices are included in the system, because currently it's not done, and we have not a big state-of-the-art on this part, so it could be interesting to focus on this part. And then we have analyzed a recent database, particularly with the channel impact, and the conclusion is WYSIWYG database is very interesting, but we need more flexibility, and to address this problem, we propose to use RiFyFi virtual generator to use parametrics model and offer large flexibility to explore database design. Thank you for your attention, and I'm here to answer the question.
Yes. When you are learning right now, you are saying that you are learning the channel and you change the channel. But when you are learning with a single receiver, you are also learning the fingerprint of the receiver.
Yeah.
Did you try to have multiple receiver to try to avoid this learning job? Because you would need to learn for every device.
Yeah. So when I present the work about WYSIWYG here, we have tested because WYSIWYG offer the possibility to, for example, do the learning with the different receiver at different locations. But the problem here is that we have two problems here, because, for example, if I try to do the learning with transmitter 1 or transmitter 6, even if they are very close, the channel is not the same. So this is the point of the flexibility. We want, in perfect case, we want to have the transmitter 1 and 6 at the same point to be able to learn and do the data augmentation of the receiver with just one position. Je vais passer en français, ce sera beaucoup plus fort. En gros, notre problème, c'est qu'on l'a fait, mais la problématique aujourd'hui, c'est que quand on fait ça, la base de données WYSIWYG, qui est la base de données la plus complète, en fait, elle nous permet de le faire, mais avec des radios qui sont à différentes positions. Et donc, en fait, on a le problème du canal plus le problème de la radio. Donc, ce qu'on a pu montrer, quand même, qui est intéressant, c'est que si, par exemple, on prend la radio 1 et la radio 6 en considérant qu'elles sont assez proches, donc problème de canal, bon, on peut se dire que c'est pas si important que ça. Donc, on prend la radio 1, on apprend sur la radio 1, et puis on vient tester sur les données de la radio 6. Ça marche pas très bien, mais ça marche mieux que si on prend la radio... Ça marche mieux que si on fait l'entraînement sur la radio 7 et qu'on vient tester sur la radio 9. Parce que la radio 9, c'est pas la même référence de radio. Et donc, du coup, ça marche un peu mieux dans ce cas-là que dans ce cas-là. Donc, dans le cas de 7 et 7.
Ça fait que ça a pris quand même un petit peu avec le fingerprint du receiver, qui varie plus entre deux références, même si a priori sur la même référence, ça devrait quand même varier aussi.
Sur la même référence, enfin, en fait, probablement que ça varie et c'est peut-être aussi ça qu'on voit entre 1 et 6 ou entre 2 et 7. Mais en fait, comme il y a aussi le canal, bah, pour pouvoir voir à quel point ça varie, il faudrait que 1 et 6 soient vraiment à la même place. Et c'est aussi une des problématiques qu'on a avec la base de données musique, c'est qu'elle est vraiment large pour une base de données radiofréquence et c'était vraiment cool de l'avoir, mais en fait, c'est pas encore suffisant, quoi. Donc, c'est un peu le côté... c'est bien les bases de données réelles, mais ça offre pas toute la flexibilité qu'on aimerait, quoi. Merci pour la question.
D'autres questions?
J'ai une question, mais je pense plus de compréhension. Donc en fait, là, quand tu dis que tu as des modèles, c'est uniquement pour la classification. En fait, les signaux, ils sont toujours réels. Qui sont utilisés, non?
Non, en fait, l'idée, c'est vraiment de venir créer on vient créer des signaux.
Ah, on crée des signaux, d'accord.
En fait, tout ça, c'est modélisé.
D'accord. Et du coup, alors, est-ce que là, vous êtes sûr que c'est un bon modèle par rapport à des signaux réels?
Alors ça, c'est vrai que c'est une bonne question. Le point qui peut... Enfin, disons que je vais répondre en deux temps. Il y a déjà le fait que les modèles qu'on choisit, c'est des modèles de l'état de l'art et qui ont déjà été utilisés par d'autres. Donc, a priori, déjà, on s'accorde là-dessus sur dire qu'on ne prend pas des modèles qui sont complètement aberrants. Après, il y a un autre point qui est quels sont finalement les paramètres que je viens choisir et notamment ces paramètres-là, les paramètres de valeur moyenne et puis comment j'oscille autour de ces valeurs-là. Ça, c'est vraiment une question. Enfin, j'ai pas mal regardé l'état de l'art pour pouvoir choisir les paramètres. Et c'est vrai que, a priori, on est à peu près autour de ces valeurs-là, mais enfin, c'est vrai que c'est assez compliqué de savoir. Par contre, ce qui est intéressant, c'est de voir qu'en fait, les résultats qu'on obtient aujourd'hui en simulation, c'est des résultats qui sont déjà obtenus dans l'état de l'art avec des bases de données réelles. Et on arrive quand même à montrer que la base de données réelle, et ben en fait, les limites qu'on trouve à la base de données réelle, on arrive à les expliquer grâce à la base de données virtuelle aujourd'hui. Donc ça, c'est un point intéressant.
Ok, merci.
Oui.
J'étais juste intrigué par les courbes d'entraînement. En fait, c'était surtout au niveau de la vitesse d'apprentissage.
Ouais.
Et ça apprend très vite. Au niveau du temps, ça va pas mal.
Peut-être c'est celle-là.
Ouais, même celle d'avant où tu montrais les TPG, tu parlais au CNN avec GPU. Donc vraiment, on voit typiquement que le GPU, il apprend en à peine une minute et ça va étonner. C'est pas tellement une question.
Ouais, en fait.
C'est pour être sûr que c'était bien le temps d'apprentissage.
Ouais, c'est bien le temps d'apprentissage. Après, ce qu'il faut savoir, c'est que ici, on n'a que 6 radios.
Ouais.
Et enfin, du coup, les signaux de 6 radios, et on n'a que 1000 signaux pour les 6 radios. Et enfin, du coup, c'est une époque qui est très rapide, en fait. Donc, c'est pour ça que ça apprend aussi vite. Et puis, il ne faut pas oublier qu'il y a aussi probablement des informations de canal qui viennent choper beaucoup plus vite que seulement des imperfections. Donc, du coup, forcément, le réseau apprend a plus de facilité à séparer les différentes radios.
Ok.
Oui.
Pour revenir sur la question de Luce juste avant, le modèle, en fait, vous pouvez apprendre ce modèle que vous contrôlez complètement. Est-ce qu'il serait capable de faire quelque chose, un petit peu de transfert, commencer à apprendre sur le modèle et ensuite transférer ça sur une plateforme pour pas que vous envoyez votre plateforme qui va faire l'identification et qui soit potentiellement lente à apprendre. Je ne sais pas où c'est lente à apprendre sur ce canal.
Alors, je vais réexpliquer la question et si jamais c'est pas ça, tu me dis parce que je suis pas sûre de bien comprendre. Mais est-ce que l'idée c'est de faire l'entraînement sur notre base de données virtuelle et ensuite on aura fait un pré-entraînement et de prendre le réseau à cet état X et ensuite d'entraîner sur des données réelles et d'utiliser le réseau entraîné à l'état X. C'est ça l'idée ou...
Est-ce que ça pourrait aider en tout cas?
En tout cas, c'est une des questions qu'on se pose justement. Donc pour l'instant, on l'a pas encore fait, mais on s'est posé la question de le faire et c'est encore là. S'il y a le temps dans la vie qui arrive, pourquoi pas. Et c'est une des milliers de portes qui sont ouvertes.